Okay, so this is the last lecture for me. So we'll continue discussing the evolution of dispersal. I don't have the pointer. So yesterday we discussed how the evolution of dispersal could be understood as selection for a mechanism to avoid crowding. And so there's a huge literature on that, on dispersal evolution, both from an experimental and theoretical point of view, more on an experimental point of view, I must say. But there's also some confusion in the literature about that, because dispersal can be understood as a mechanism to avoid competition in general, but also kin competition in particular. And we'll spend some time today discussing that. So I'd already mentioned to you this experiment with seeds and this plant that have a structure that facilitates dispersal by ants. And in that same experiment, I don't know if you remember, but there was a color code for each family of seeds that were deposited at the bottom of each mother plant. So by recovering the seeds after dispersal, they could also see, using this color code, they could compute the fraction of seeds in the neighborhood of each seed after dispersal and before dispersal. And this is what is indicated here. So before dispersal, of course, all the seeds were surrounded by sieves because they were all born under the same mother. And after dispersal, for the 2 years of in which the experiment was conducted, the fraction of sieves in the immediate neighborhood of those individuals had decreased. So you had decreased relatedness with your neighbors due to dispersal. And yeah, so this idea that dispersal could be a mechanism that would lead to decreased competition between related individuals was not early an idea that was very obvious for many. Dispersal was seen mostly as a way to adapt to environments that are varying through space or time. And there was a paper in the late 70s by Bill Hamilton and Bob May that was really influential. It was published in Nature. It's a very simple model, but it, for the first time, showed that dispersal could evolve in completely stable habitats. Without any disturbance, without any variation in the quality of habitat through space or through time, which was not really intuitive for many people. So what I would like to do today with you is really derive those very simple equations to get you a feeling of what might be going on. And it's also a simple exercise to do, so we will do that together. So what this very simple model assumes is that you have an infinite number of patches in the landscape, so a very, very large number. Each of these patches can contain a single individual, adult individual. In other words, there might be a lot of offspring in any patch at the beginning, that at the end of competition, there will be only a single adult reproducing in each patch. Those individuals produce a very large number of offspring. After they reproduce, they die, and they free the site that they occupied previously. And among this very large number of offspring, a fraction y minus d stays in the nettle patch. And fraction d disperses out of the nettle patch. So all migrants from all the patch in the landscape are mixed together in a large migration dispersal pool, and they are randomly distributed all over the landscape. So it's the island model of migration that I mentioned before. A fraction C of this dispersing offspring dies in the process of dispersing, and fraction 1 minus C survives the dispersal episode and actually lands into some patch where it can potentially grow if it succeeds in competing with other individuals in this patch and winning the patch. So after dispersal, immigrant and Kilpatrick individuals that are in the same patch compete to establish in that patch, and only one will be chosen to establish in that patch. And there's a fair lottery competition, so just one is chosen at random among all those competitors. So there's no advantage of Kilpatrick individuals in this model after immigration. So it's called a fair lottery competition. So those are the assumptions. Now let's imagine two types, two alleles. One was dispersal rate. So let's say we have big M allele with dispersal rate V, and a little M allele with dispersal rate D star. And let's assume that we have an haploid model and we don't have to worry about diplogenetics. So this model was extended to other cases afterwards, but the simple idea is there. So let's do what we did before, which is let's compute the expected number of offspring of some variant with dispersal rate D star in a population where most individuals have the other alternative allele big M and have dispersal rate D. So this is the expected number of offspring surviving offspring So, if we want to compute that number, let's say the fecundity is F. What do I have to sum? If I want to compute the expected number of the offspring that a given mother will produce, and the number of surviving offspring, what do I have to count? What type of offspring does this mother produce? What are the types of offspring? You don't see, or you're just too boring? Sorry? Yeah, but just before that, I mean, what are the types of offspring that a mother produces? Those dispersed and those not dispersed, okay? So what is the fraction of the offspring of this mother that are not dispersed? One minus D or D star. Okay? And then what we will need to do is compute the probability of survival, okay, of those offspring that are Fitzpatrick. Then, what are the other type of offspring? The dispersers. What is their fraction? And what do we have to multiply this by? 1 minus C to account for the fact that some of those will die, and then the survival of dispersing offspring on average. So let's compute those survivals, okay? So the probability to survive and reproduce, so to be the one chosen among all others to reproduce in natural batch, is equal to what? So I've got a number of offspring that are going to be in this natural patch, and I will pick just one to survive. What would be the survival probability for each of those individuals? If I call n after dispersal, the total number of offspring that I expect in that batch after dispersal, what would be the probability to survive for any of them? 1 over that, okay? So how many will I get in that batch after dispersal? Now, what are the type of offspring I will find in that batch after dispersal? So I will find the non-dispersed offspring of the local mother, okay? And those who came in. So let's first compute how many offspring from the local mother do I expect to stay in the patch. 1 minus D or D star? D or D star? Who's the mother in this patch? What kind of allele does she have? computing the fitness of somebody with L in M, okay? So how many non-dispersed offspring this mother will produce? 1 minus D star, okay? You have to multiply this by the fecundity. It's only one mother in that patch. So that's all the Fitzpatrick offspring Fitzpatrick individuals you will get. Now the immigrants. How should we compute the immigrants? Just to ease the calculation, here we'll assume that I have let's say big S. But the number of sites is big S, or number of patches. And then we'll take a limit when this big S goes to infinity. Okay, but maybe to compute, it will be easier to imagine that there's a finite number of patches. So what is the number of immigrants that we expect to arrive in this patch? Who's going to send migrants to this patch? All the other patches. So how many other patches is there? So let's wait. One way to do it. Okay, here you're assuming that because well, we could do it this way, but we could also assume something different. Like here, what I said is that every site is sending migrants to a big migrant pool, and then it's distributed completely randomly across the landscape, which means that they can come back to the site where they were. But we can also do it this way, which is a bit different, because here your assumption is that all the migrants are mixed together and they are distributed to all other sites except the site they were born into. So the two are possible. Actually, it will end up to be the same if S is really large. So let's try with this. So if we do that, there were S minus 1 sites that sent migrants. How many migrants each of those sites produced? D star? Why D star? Who is in these other sites? So we were dealing with the fitness of a mother. We know that this mother has LM. But now we're dealing with all the other sites in the landscape sending migrants to that patch. Do we know about the genotypes of those other individuals? We do not, but we assume that what I say that the most common genotype in the landscape is what? It's big M, okay? So on average, if this genotype is really more frequent than little m, what would be the number of migrants sent by those other sites? In this other site, what would be the dispersal rate? D, okay? Then, what do I have to do? Well, first, I have to multiply by the fecundity because, okay, that's a fraction of dispersed offspring, the number of offspring each patch produces. In each patch, there's only one mother. And then what happened to these dispersing guys during dispersal? They have to survive. So what is the probability that they survive? Okay. But this is not all. This is the total number of migrants that are produced in the whole landscape. Now, this is not the number that this patch will receive. Okay? What do we have to do? This is the total number of migrants that will be produced. We have to divide by, okay. So it depends what we want to do, but we could divide by s minus 1 or by s if we assume that they're distributed all over the place. But it's, let's say we divide by s minus 1. So it means that this disappears. If we divide by s, it disappears only if we take later, if we take the limit of s going really large. Alrighty. Okay, so here my survival then will be 1 over f So let's make the same computation for the probability to survive and establish in a site if I disperse and I successfully immigrate in some other patch. Okay, so by the same arguments, it's going to be 1 over the number this time after dispersal still, but elsewhere, not in the nettle patch. So how many individuals will we get in some other patch where another mother was reproducing was probably not the same genotype as the local mother? What will you get? So is it what? Is it 1 minus d star or 1 minus d this time? If I go to some other place, what would be the likely genotype of the mother there? Big M. So what would be the fraction of philopatric offspring in the progeny of that mother? 1 minus d. And the number of immigrants is the same everywhere, okay? So if I add up all this, the fitness of a mother carrying little m in a population where most will carry big M is going to be okay, so now we've got this fitness. And what we want to look at to find is a strategy, the best strategy for M, for L big M. We want to find the dispersal rate that if it is the dispersal rate of the dominant genotype in the population, no mutant or no other genotype with a deviant phenotype can invade that population. Okay? So do you remember from yesterday how we do that? What we want to find is that we want to find the strategy D, or let's call it, I don't know, the hat. That the fitness of any phenotype is smaller or equal to the fitness of the resident genotype. Which means that this is the maximum of this function. So can you tell me how you find such a maximum? Remember that? How do you find the maximum of function in general? Can you speak out louder? And the first is? Okay. So so what means is that this function of D equal, D star, has a maximum at D star equal D hat. So there are different, so it's, what you say is true, but there are also other ways to get a maximum when you have a range of phenotypes that is limited. So if D hat is strictly between 0 and 1, then indeed what we need to find is a value or if the other option is that if this is also a maximum, because the minimum value of the dispersal rate is 0, okay? The dispersal rate is a proportion, it must be between 0 and 1. So if we find that at 0, the derivative is negative, so it means that the function is something like that, the fitness function. And so it means that the maximum here is 0. So you don't need to be at, you don't need to cancel the first derivative in this case. And for the same kind of argument, if D star equal 1, then the only condition for it to be maximum this is positive. So in this case, you've got one here, you've got something like that, or something like that. So let's compute that derivative. Maybe I should do that on the other board. Okay, so can you tell me how to derive this? So we have to derive with respect to d star, okay? This is a function of d star. So the d here will be assumed to be constant. So we have d star here, d star here, d star here. You remember what is the derivative of the ratio of two functions? Want me to remind that? So yesterday we saw that the derivative of xy product some quantity was equal to x if you take the derivative of some ratio of function, you have something like that. Okay, so well, let's derive this term, which is easy. First, who can give me the derivative of that with respect to d star? So basically here I've got, if I take only this bit, I've got only d star here, and it's nowhere else. So I just have a big number multiplied by d star. So if I take the derivative of that, what do I get? Just this number, okay? And yeah, we forgot to do something, which is we can simplify this because we see f is here and here all the time, okay? So we can remove all those f. We don't need the f. So I get y minus c. Then, can you tell me? Okay, it was an easy bit. Now the first term. Okay, I'll write it to you, for you. If you compute it, I'll give you just the result. 1 end up with having this. If you rearrange everything, you find this. So if the cost of dispersal is smaller than 1, which means that at least a tiny, tiny bit of the dispersing offspring survive, not all of them die, then this is going to be greater than 0. And if you want this to be 0, this side here must be 0. This quantity must be 0. Okay? What is the ESS dispersal rate then? What is the strategy that is maximizing and resisting invasion from enemy? If this is 0, what is the value of Z? 1 over 1 plus C. The other thing we can do is that, so let's look at that. So the ESS for dispersal rate, so the evolutionary stable strategy, able to resist invasion by any other mutant with a different strategy, is simply 1 over 1 plus C. So this obviously, what does it do when the, so it depends on only a single parameter, which is the cost of dispersal. And what happens to this best dispersal strategy when you increase the cost? Does it increase or does it decrease? You increase C, what happens to this? It decreases. So it decreases if the cost of dispersal increases. Pretty logical. But if we take the limit when C goes to 1, which is the maximal value, okay? So when it goes exactly to 1, it doesn't mean anything. So this is, when it goes exactly to 1, this gradient is 0 anyway. So any, but if it's very big and almost 1, what is the value of the evolutionary stable dispersal strategy then? If C is close to 1. 1/2. So it means that under the assumption of this model in this landscape, a mother should disperse at least half of her offspring out of the nanopatch, even though almost all of that offspring would die, have a certain death, okay? And if the dispersal cost is a little bit smaller than this maximum value of 1, then you should disperse more than half of your offspring out of your adult patch. So, and the second conclusion is, if you look at the fitness function on this, the ESS for dispersal rate can never be 0, okay? Unless the cost of dispersal is 1 exactly, and then it doesn't matter what you know, because then there's no dispersal at all in this system. So this was very surprising. So as I said before, historically people really thought that dispersal was an adaptation to ephemeral habitats. And finding that in a perfectly stable habitat, homogeneous, I mean, we did not assume anything different from any patch. All patches are the same. You predict that mothers should disperse a huge fraction of their offspring all the time. And it's quite unclear what is the benefit. So, okay, so these results come out from very simple equations. And in this model, there's no benefit for the offspring to disperse. No, by dispersing, you will end up to find the same habitat quality as where you were born, but you're going to risk death by dispersing. So from the point of view of the individual dispersing, it has absolutely no fitness benefit to disperse. When we computed the fitness of disperser, if there was the same genotype everywhere, the fitness of a dispersing offspring, once it has immigrated, is exactly the same as the fitness of a non-dispersing offspring that has stayed in the patch. So there's difference because of the cost, but once you have immigrated somewhere, you have the same prospect of surviving if you don't have any different genotype in the different patches. So this led to, but despite that, a mother is selected to disperse a lot of her offspring. And this led Hamilton and May to argue that in this model, dispersal evolves not because it's a benefit for the individuals that disperse, but because it's a benefit for the mother who's dispersing her offspring. And that actually, by dispersing, individuals compromise their own fitness, but for the benefit of their shipship that remained in the home patch. So you can see that, well, unfortunately I've erased the function, but you can get some intuitive feeling about it. If you look at the fitness function for Philopatrick. Which was something like that. Okay, so the only difference between this and this is this term here. And if your mother has a higher, disperse more of her offspring, okay, so this is smaller. If the number of Philopatrick offspring remaining in the patch is smaller, this whole number is smaller, so the survival probability of Philopatrick is bigger. So the survival of Philopatrick offspring is bigger for those who belong to a genotype that is more dispersive. And this is why dispersal is selected for in this model. So when, yesterday we wrote this equation where we had, I can come back to that. Okay, yeah. So we wrote this selection gradient in general. So that's what we did here. And this is just a special case of that. Because what you can see is that this term here is all in this model is always negative because on average, if you take the same, if you put the same genotypes everywhere, this negative number is bigger than this number because you've got the cost of dispersal. So you've got here the direct difference in survival between Fitzpatrick and dispersing individual is selecting against dispersal in this model always. But the reason why you get this positive selection gradient potentially is because of all the terms. It's because the fitness of the Fitzpatrick offspring on average is depending on the identity of the focal genotype. So, because in this case, it's an extreme case of genetic structure because there's only a single mother per patch. So if your mother has some dispersal rate, you can predict exactly what will be the number of Fitzpatrick competitor you will face. And if you disperse to some other patch, otherwise you will be confronted to a different mother with a different dispersal rate and a different number of competitors. So selection is only due to this indirect effect of your fitness depending on the identity of the genotype you compete with. And so you can generalize this very simple Hamilton-May model to a system where you would have, so this is another, a cartoon argument for what I explained. If a mother, this green genotype is dispersing more of the offspring, then there will be less offspring remaining competing in this patch, and more competitors in the other patch that are where mothers with a different genotype are born. So if you generalize, so in this island model, the number of immigrants in every patch is the same. That's what we wrote here. So every patch receives, on average, the same number of immigrants. Then if you start to have some stochasticity with some patch receiving no migrants and some patch receiving less migrants, and there's another layer of complexity on that. But here you assume that the number arriving are the same for all patches. Okay? Is that answering your question? So in this model, so you're always picking one. So I agree that you look at this fitness here. So the only way you can vary this number of immigrants in each patch is if the dispersal cost is different or the average dispersal rate in the system is different. So if you have a genotype that is already dispersing a lot and the dispersal cost is small, this number is going to be big. So it's true that on average it will be a higher chance that it will be an immigrant that will be picked up to become the next adult reproducing there. But it does not change the fact that there will still be a small difference between the patches that have, so the strength of selection is going to be weaker when you get close to the ESS. But there will still be, the sign of selection will always point in that direction. So now so what did people after this model is try to generalize that to a system where you would have patches containing more than one individual. If you assume that you've got patches with a small, again, the same number of individuals, a finite number of individuals per patch. Then, if you do the same kind of computation as, so again, if I go back, so I do the same kind of calculations, except here, what I compute this. I'm going to have something slightly different. Because here now, I will have 1 minus d0 okay, well, this is a dispersal rate in my home patch, but this is not just set by my own genotype, because there are other females reproducing in the same patch, okay? And this is a dispersal rate in some other patch. And if I disperse to some other places, then I will have something like that. Well, this is a dispersal rate, average dispersal rate in a patch that is not my own patch. I know that I'm not in that patch. And a number of immigrants, this is also the average number of immigrants that all patches are receiving. And so the computation of this is a bit different, but basically it's the same argument as I explained yesterday, is that if you want to predict the dispersal rate of your neighbors, it's going to be something like that. Where, you know, I assume that little m allele has a dispersal rate d plus delta and big M. And d1 so what this Q is a probability to draw identical genes, copies, in two individuals in the same batch. Okay, so if I reproduce in a patch with n-1 other females, I know that I'm one of them, so I'm contributing offspring to the offspring of this population. But those other females, they might actually carry the same gene as I do, if there's been some structure, genetic structure. So if they carry the same gene as I do, I can predict what the dispersal rate is. And then I will not have the same survival of my offspring in that patch as in some other patch. Because the very fact that I know that I'm in that patch is predicting what is the dispersal rate of my neighbors. So this is why when you do that, what people found is that this time the SS dispersal rate were finding that this could be expressed in a very large class of model as R minus C, R minus C square, where R is the relatedness between individuals in the same patch, which is defined by the difference in the probability of identity between pairs of individuals that are either in the same patch or in different patch. scaled by basically an idea of the genetic diversity in the whole system. So this was kind of nice because when you wrote this equation, you really find expression for the selection gradient on dispersal that really looks like Hamilton rule for the evolution of altruistic behavior. Like you've got some R, some relatedness, some benefits of this altruistic act, and some cost of it, which is the cost of dispersal. And so you end up with expression that really show that dispersal evolves, has cooperation or altruism could evolve in other systems. But there's nothing magic about that. It's just that in all those situations where there's genetic structure, you could also see it simply by the fact that your own fitness is going to be affected by the genotypes of other individuals around you, and those genotypes are correlated because genetic structure is creating association between the genotypes of individuals through space. So the difficulty then is that so you can write things like that and helps you to understand the type of selection that is acting on dispersal, but those properties of identity, they depend on dispersal. I mean, if you mix a lot your system, there will be no genetic structure, so there will be not a higher probability to find identical genes in the same patch as in two different patches. And they also depend on the size of the patches, so those things evolve, those relatedness and probability of identity. And they're not fixed parameters that you fit into the model. They evolve together with the traits that are evolving in the model. So solving this model involves trying to write recurrence equation to compute those probabilities of identity. You can use correlation theory, as Magnus explained to you this week, to do that, to compute the probabilities of identities of individuals in the same patch or in different patches. And if you have more complex models of spatial structure, you could also compute the probability of identity of individuals in the same patch or in patches that are at distance 1, 2, 3, 4, 5, or whatever. And in this simple example of a structure where you just have, a very large number of beams with a fixed number n of individuals, you can, if you solve that by taking into account the fact that this depends on dispersal rate and this depends on those quantities, and you solve the whole system, you find that the ESS dispersal rate is this relatively complicated but not too complicated function of the population size and the dispersal cost. So very quickly, if the population size increases, the ESS dispersal rate declines, but it never goes to zero in reality, because there's always some little bit of genetic structure. So now an interesting extension of this theory is what happens if different mothers do not produce the same number of offspring. So there's, in general, very large variation in fecundity across space. And Kishdi is a nice model, where basically it's the same assumption as the model of Hamilton and May. There's only one single mother patch, but there's some random variation in the fecundity of mothers. And then she assumed that mothers could actually know what their fecundity is, and they could adjust the dispersal rate of their offspring depending on their fecundity. And she asked not what is the fixed ESS dispersal rate, what is the best dispersal strategy of adjusting your dispersal rate to your fecundity. And interestingly, she found that the ESS was characterized by producing a fixed number of Fitzpatrick offspring. So whatever your fecundity, you're going to produce the same number of Fitzpatrick offspring. And all the remaining offspring, you're going to disperse. So this predicts, indeed, that if you've got a large SIP, you have a large dispersal rate in terms of proportion, because you produce the same number of Fitzpatrick offspring, and all the other extra offspring you're going to disperse. So in proportion, you're going to have a big proportion of dispersal. If you have very few SIPs, you're going to have a very low dispersal rate, because you're going to first produce your Fitzpatrick offspring, and if there's some remaining dispersals, you will disperse them. So it's quite intuitive, because indeed, if you've got a very large number of brothers and sisters, kin competition is going to be stronger within those patches, and so there are more incentive to disperse. And this is very common, for instance, in human families, that such thing happens. Like often you inherit the wealth of the parent for some of the offspring, and the others disperse and do a job in the army or. Recently we did some experiments as well to try to see how these ideas of dispersal allowing to escape both competition with anybody and also more specifically kin competition with related individuals. So I just want to clarify something, because this idea of avoiding kin competition is very confusing in the literature. People think that it's bad intrinsically to compete with your brother and sisters because it will harm you more. Actually, it doesn't, or at least in those models. If you compete with your brother and sister, or if you compete with a foreigner, you will not be harmed more. It's just that you are harming somebody with the same genes as you. So in the point of view of genes, there are less gene copies transmitted. But from the point of view of the individuals, there's absolutely no difference. Dispersal is a way to avoid kin competition, not because kin competition is bad intrinsically for the individual, but because it's bad for the transmission of genes. Okay? So in this experiment, we use this spider mites, and we use this dispersal assay that I already described to you yesterday. And based on theory, you expect that the dispersal distance should increase with the density of competitors that we put in the first patch here. And we also expect, based on other theory, that the dispersal distance should increase with a genetic resemblance among competitors. So we manipulated both those factors, both the number of competitors and the genetic resemblance. And we recorded the whole dispersal kernel, and here's what we found. We found that dispersal distance increases with density. So indeed, it might move further when they are initially confronted to a higher number of competitors. So it's okay. So that's the mean dispersal distance, but if we look at the shape of the dispersal kernel through its kurtosis, we find no effect of the density of individuals in the starting patch on this shape. So basically, if you increase competition, all the mites move further, but there's no change in the distribution of dispersal distance. The shape of the dispersal kernel is not affected. If this time we manipulate the genetic resemblance among competitors by mixing different inbred lines and computing their kinship coefficient with some genetic markers, we have a relationship between the mean dispersal distance and the kinship coefficient among competitors in the starting patch. So again, if you compete with individuals that resemble you from a genetic point of view more, dispersal distance increases. And this time, we also find an effect on the shape of the dispersal kernel, which change with the genetic resemblance of competitors, suggesting that probably those individuals that react to kin competition are not a random sample of the population. So, and probably a few mites move really further, but not all of them, which we do not predict with theory at the moment, but is an interesting thing to explore. So now, inbreeding avoidance. So also a large part of the literature about dispersal been discussing the role of inbreeding avoidance in the evolution of dispersal. So this was motivated by a number of experimental studies. I'll just tell you about one. In this little rodent, if you remove parents of one sex before the typical moment of dispersal for the offspring, you find that offspring of the opposite sex disperse later. Just as if, in your control, the presence of parents of the opposite sex was the motivation for those animals to disperse fast. And this was interpreted as like those male or females, they don't want to mate with their mother or with their father, so they escape the population to avoid inbred mating. The idea that breeding might be really important to understand dispersal is also supported by the very frequent observation of sex-biased dispersal. In many, many animals, either males disperse and females do not disperse, almost do not disperse at all, or the reverse. It varies among groups of animals. And even in plants, if you think about it differently, pollen dispersal distances are completely different from seed dispersal distances. So you also have different dispersal of the male and female components somehow. And even so, it's a bit more complicated. So there's been a lot of debate trying to explain sex-biased dispersal with opposite arguments saying, yeah, it's because of avoidance of inbreeding, so one sex disperses always and one sex stays, so this way you avoid breeding between related individuals this way. And some others say, yeah, but it's not the explanation. The explanation is that you've got sex-specific competition. So, for instance, if you've got very strong competition among females, then females will be the dispersing sex, and males will not disperse, or the reverse. And again, this sex-specific competition could be also sex-specific kin competition, depending on the social structure of those animals. So, first of all, why is it good to avoid inbreeding? Because it's not completely obvious. So there's quite a lot of data suggesting that indeed, when you do crosses between individuals in the same population, or crosses between individuals belonging to different populations, in some cases, in some populations and species, you get a higher fitness when you do crosses between populations that belong to different populations. And but you can see that there's some variation still. For some population, they actually perform a better fitness when they cross within the population than with some other population. And what is a common observation is that so this phenomenon is called heterosis. The fact that when you breed, when you cross things that are that have been separated, you get a higher fitness. And what is very often observed, and is the case in this example, is that heterosis, so the gain in fitness when you do crosses between populations, is much higher in small populations. So for there to be a benefit of dispersing out of a population to find mates with whom you're going to mate and produce offspring with better fitness, you need to disperse out of a small population. Otherwise, there's not much benefit to do that compared to the cost of dispersal. So these observations are completely consistent with theoretical expectation, and those theoretical expectation is that heterosis between populations like this is due to the fact that small populations are fixing due to drift different deleterious mutations that are recessive, and that when you cross those mutations, so different populations fix different deleterious mutations because it's just the effect of random drift. So there's no reason why they would fix the same deleterious mutation. And when you cross them together, you restore heterozygous genotypes that have a higher fitness because they match the effect of those recessive deleterious mutations that were fixed in any of the populations. And so the prediction of different models is that this level of heterosis depends on the mating system, so the selfing rate, for instance, in the population, but also critically depend on the number of migrants in those metapopulations. And so heterosis is big only if this number of migrants here is really small, which means that if either the population size is really small or there's a very low number of migrants. So, or a low probability to migrate. So the number of migrants must be small, so either through small population size or low dispersal distances or ability. So again, you can see there's a feedback because so dispersal, the benefit of dispersing will depend on heterosis, but heterosis depends on the level of dispersal. So if you disperse a lot, you do expect no heterosis anymore. So some models have tried to, so initially, all those components were seen as fixed properties, like the inbreeding level would be something not evolving and so on. And some models in the early 2000s have tried to revisit that and try to model all those complicated interactions. Because actually one conclusion of those models is that you actually cannot separate the effect of heterosis and inbreeding on the evolution of dispersal from the effect of kin competition. Because you will have heterosis only in small population with low dispersal rate, and this is also the condition where you're going to have a lot of kin competition because you're going to have a lot of genetic structures. So anytime you've got a strong heterosis and inbreeding, you also have that. So those two assumptions that individuals disperse to avoid inbreeding or competition between relatives of the same sex cannot be separated. They will always occur together. So there's no point trying to say this is the explanation or this is the explanation because everything will occur together. And then there are complicated feedbacks because the dispersal rate in evolving is changing the relatedness in the population, also changing the heterosis. The population size affects both, and this is quite complicated. But there are some models about that if you are interested. And so I think still here, what was, still in those models, I think they assumed that this inbreeding depression, the inbreeding load was fixed. And then later there was models that were a bit different, multi-locus models, where you've got one locus that is affecting dispersal behavior, or dispersal modifier locus. And you've got a second locus, which is affecting the viability of offspring with mutation that can be recessive and deleterious. And what you look at there is a joint evolution of the inbreeding load and the dispersal rate. And you have to take into account the recombination between those two loci to understand what is going on. And what they predict is, indeed, if you increase the rate of genomic deleterious mutation, so you have more input of deleterious mutation in the system, you will evolve higher dispersal rate. So there's another aspect that has been little considered by those models, that inbreeding might also affect dispersal through direct effect of inbreeding on dispersal behavior. And this is an experiment in spiders in the group of Gisponte. And spiders have two modes of dispersal. They can do rappelling with their silk, which is just short distance dispersal. And they can also do something called ballooning, also using silk. They are drawn by air currents, and they disperse further, especially in the fall season, through this process. So in this experiment, they were able to record short and long distance dispersal for 3 species of spiders that were either outbred or inbred. And both for short and long distance dispersal, they found that outbred spiders disperse further than inbred spiders. Okay? The black bar are inbred spiders. So inbreeding, by affecting a lot of phenotype, is also affecting directly the expression of the dispersal phenotype, probably because inbred spiders are just crappy, and so they can't disperse. So it might also be more feedbacks that envisioned by the previous models because of the direct effect of inbreeding on dispersal. So finally, I will discuss a little bit how dispersal might be seen as an adaptation to ephemeral habitats. Because again, there's a lot of confusion in the literature about that. So to me, there are different situations where actually dispersal can be understood as an adaptation to ephemeral habitat. There are situations where there are random fluctuations in the quality of habitat through time and space. We already discussed that. So, and in those circumstances, To me, at least the models that have tried to explore that show that dispersal evolved as a way to avoid crowded conditions. And the variation in the quality of habitat is just producing a different availability of resources through space. So we've seen that already, but I'll just explain. No, I won't explain. So the idea is that if you've got random fluctuation in patch quality resulting in random fluctuation of density, at any point in time, you might have variation in density through space, which is not indicative of future density in space. And so there's a benefit to send migrants away from the very dense patch towards the other patch, because there will be a net flow of individuals from crowded patch to less crowded patch. And if the condition the year after that are not predicted by the current density, then there will be an advantage to be in a low density patch, because you might have a lot of resources with very few competitors. So in all those models, I think this is the main reason why dispersal evolved. Then there's another argument, which is based on bed edging, which was actually really shown in few models, but is claimed as an argument explaining the evolution of dispersal in many, because it's a nice concept, but I don't think it's actually, so it might be important for dispersal evolution, but in those models, I'm not sure it's playing any role. So the idea here is different. So the idea is there's also random fluctuation in the environment. And if you are in some patch, and there's every year some disturbance occurring at random in the landscape. If you do not disperse your offspring, and it's a disturbance, so you keep all your offspring in their home patch. If the disturbance hits some other patch, well, you win, because all of your offspring survived. But if you're unlucky, and the disturbance arrives in the patch where you put all your offspring, all of them die. So it means that on average you could have the same average success, but you're going to have a high variation in your success if you do not distribute your offspring in space. While if you do that, if you disperse your offspring, okay, here I put my offspring in every patches. If the disturbance hits this patch, I will lose some of my offspring. But if the disturbance hits this patch, I will still have some offspring survive. So in this model, they show that indeed this kind of mechanism could explain the evolution of dispersal or seed dormancy and other strategies of bed hedging. However, for this to work, you need to assume that every genotype is distributed in a very limited number of sites. Otherwise, just by being everywhere, you're already bed hedging, because you already have genotypes in every in all sorts of patch. So you don't need to increase your distribution through dispersal. So I'm not saying that this is not important in reality, but I'm saying that a lot of models do not have this property because they assume an infinite number of patch, and that every genotype is everywhere. So this is not working in explaining the result of those models, but it might work in explaining evolution of dispersal in nature when genotypes are indeed distributed in a finite number of patches. There's another reason why ephemeral habitat favors the evolution of dispersal, which is barely discussed, and I think it's quite important, is when change in environment is actually predictable. So for instance, in many species, there's either ecological succession, where you can actually establish in some environment that is favorable at some point and degrade through time because other species come in, or the population, the vegetation is growing, and so the quality of the habitat is declining on some predictable way through time. This is true for plant species in succession, but it's true as well when you are, a beetle that is exploiting some carrion, and these host resources will degrade through time. And there's many, many ephemeral habitats in nature that have this property of being good, or rotten fruit for a fly, for instance, that is good at some point, and it's degrading through time. But this degradation is predictable. And then dispersal is the only way to escape those degraded habitats. And so this was, to me, explicitly modeled by this model by Isabelle Olivieri And since then, not really much discussed in the theoretical literature. Well, I think it's really important. So the idea is very simple: is that if you are a colonizing plant that you like open vegetation or a lot of light, then trees progressively colonize, and this becomes a forest. Well, if you don't disperse, you will never reach those empty patches with lots of resources that are the habitat that you like. So, about experiment testing those ideas, there's been a very nice paper by Emmanuel Fraunhofer a few years ago, where he also uses spider mites as a system to, this time, let dispersal evolve in some kind of experimental evolution system. So he had a kind of metapopulation, set of patches made of leaf caps, were connected by bridges where the mites could disperse. And he had different treatments: a treatment with no extinction, a treatment with, he had some random extinction, so he would take the leaf and throw it away with all the mites that were on it and replace it by a new leaf, or some treatment of clump extinction, where when disturbance occurred, they were not occurring at random throughout the landscape, but in a clump manner. And it did that for 10 generations, and after those 10 generations, it took the mites that had evolved in those conditions and did dispersal assays to look at how their dispersal kernel had evolved. So it did two things. So he looked at the empirical data, but he also ran a little simulation, simulating the same system to predict what would happen. And so the model predicts that, so in the control system, you should evolve very little dispersal. So if you have random extinction, then you should have more individuals dispersing, but they generally disperse a short distance, like just one patch. And if you have clump extension, what is interesting is that you have less individuals leaving their initial patch, but those that go, they go further. So you have less, if you want, dispersal rate in terms of leaving the nano patch, but greater dispersal distance. So this is interesting because you see that dispersal distance and immigration rate are potentially different characters that could evolve differently. And this is exactly what he found in the experimental data. So in the empirical data, he found that indeed the control dispersed very little, the random extension dispersed essentially short distances, and the clump extension treatment dispersed less, and when they disperse, they go further. So finally, so we discussed this cost of dispersal many times, and so it's not completely clear what this cost is. So in the model, it's always simple, it's like you die, but actually there are many other costs of dispersal. So first of all, dispersing individuals often don't have the same trait at all as the philopatric individuals. They may have different morphologies, have lots of different aspects of their phenotype, they often have different life history. And whether this is a cost or not is not always completely clear, but this is just one example. So, I told you yesterday about the cane toad expansion. And so that it was an evolution towards greater dispersal in population that were recent, so at the edge of the expanding age. But if you look at other traits, such as the proportion of females laying eggs, so the fertility of females, you find that those females with a very good dispersal abilities at the edge of the range also have very poor fertility compared to females that you find in more established populations. So the question with all those correlation between life history trait and dispersal is whether those express a cost of dispersal, like do those animals that have very big limbs and disperse very far allocate resource to that and they don't have resources to allocate to fecundity, or are they selected to have a very different life history strategy? So is this syndrome an adaptation or just a cost and a constraint? And it's really difficult to tease apart those two explanations. And I recommend for you this review that was published relatively recently about cost of dispersal. There's also a book chapter that I did with Jean Claubert on syndrome, dispersal syndrome. That might be. So those costs are not simply the cost of, so you could have different traits as the dispersing individuals, but you could have the same traits that still have a cost because dispersal in itself is very risky. So you can die on the way, but you can also die once you immigrated. And so because foreign environments are often dangerous. And they are dangerous for many reasons, because you change your social environment. So for instance, in those mole rats, there's very, very high xenophobia. And so those animals are colonial, and they also work collectively, so it's kind of what do you call that? You social insect, social animals, with only a couple reproducing and the other workers, and they basically hate newcomers. So dispersing individuals, if they meet with some workers from a foreign colony, generally they are completely destroyed and killed, and they have to get in quickly into the main chamber of the colony to get the smell of others on their skin and to have a small chance to survive. Then another reason why it might not be a good idea to try to go somewhere else is that you might lose all your social interactions, and this is very important for fitness. But you might also lose your local adaptation. And this is an experiment with some plants where they took seeds that were either outbred or inbred and transplanted them at a very short distance of the mother plant. And they found that, especially for inbred seeds, the fitness of the offspring declined very quickly when they moved away from the location where they were born. So probably because this plant is adapted to very specific environments along riverbed, along the river edges, and that it suffers a lot, even at a very short distance, of different variation in environmental conditions to which it's not adapted. So last question, I will finish, is so we talked a little bit about many different factors and a little bit about dispersal distance. And it's not, so the literature for a very long time focused on this kind of dispersal rate that we manipulated here without really thinking about, does it matter how far you go? And so intuitively you could imagine that those different selective forces act at different distances. So maybe, if the main reason to disperse is to escape parent-offspring competition, you don't have to go away very far to do that. If you want to escape competition with individuals that share the same genotype as you, maybe you need to go further. And if you want to avoid breeding with relatives, you probably also need to go further. If you want to escape crowding in general, maybe you need to go even further to escape that. And if you want completely to change habitat quality, maybe you need to go even further. And if you go further, is the cost increasing or not with distance? Maybe yes, maybe not. So there's been more work about evolution of dispersal distances that show that those intuitive ideas are not necessarily true. So for instance, this is a model by François Rousset and Sylvain Grandon about the evolution of dispersal kernels, where the only ingredient that they had in their model was a simple, the same kind of model as this, with patches of habitats, with some fixed number of adults in them and some dispersal costs, except that now you had a stepping stone population and you were looking at the probability to disperse 1 patch, 2 patch, 3 patch, and so on. And you were assuming no constraint on the shape of those kernels, and so really looking at what is the ESS distribution of dispersal distance. And so the only force selecting for dispersal in this model is the avoidance of keen competition. And if you make different assumptions about how the cost is changing with distance, either decelerating or accelerating, you have different shapes of the dispersal kernel. But you can find fat-tailed dispersal kernels that are declining less fast than an exponential with distance, which is what is producing long-distance dispersal. And so even with only with skin competition in a very simple model and no spatial heterogeneity or whatsoever, you can already predict the evolution of fat-tailed dispersal kernels that have huge effect on the ecological properties of population, spread rates, and everything. So a question that I wondered about for a long time is that whether those short distance dispersal events that we see that can have a huge or disproportionate impact on the ecology, the spread rates of species, and so on, are they really selected for, or are they just a side effect of selection on short distance dispersal that accidentally produces those long distance dispersal events from time to time? Or is it the reverse? Are those organisms just trying to get their offspring very far away from them, and they just fail, and most of the short distance dispersal events we see are just failure to try to go very far away, and organisms will be very inefficient in doing that. So this question was quite an open question when I wrote the review, but since then, I think there's building evidence that short and long distance dispersal do have the ability to evolve independently and respond differently to various cues. And a lot of mechanistic models, for instance, of seed dispersal, suggest that different plant traits, different vectors, or different processes explain short and long distance dispersal. So potentially, these two types of event are governed by different selective force and can be considered as evolving independently, which is something that we should do when trying to understand and model. So in my review in 2007, I was pointing at issues that would be interesting to explore because they were not much explored in the literature at that time. So one aspect would be about the heritability of dispersal kernels and dispersal reaction norms to environmental cues, and this is clearly ongoing now. We pointed out this need to model the evolution of those dispersal distances, and this is also ongoing. This is less clear to me because I explained to you there was a lot of plasticity in dispersal, but I don't think we understand very well yet which information is used really at which stage to affect the dispersal kernel, and why, for instance, we see sometimes maternal effects, sometimes we don't see them, sometimes we see an effect of direct environment, sometimes not. So this is not so clear to me. Again, I think given a lot of challenges linked to the evolution of dispersal in a changing environment, we need to produce short-term prediction about evolutionary change in dispersal in the context of global change, and this is also starting at the moment. So that's all I want to say. Questions about dispersal?